by accident. But worked out.
Yeah. I ran into him at, wait, maybe he told you, I ran into him at a pitch event the other night.
Oh yeah, because he's doing a thing.
Yeah.
Yeah.
Because I'm one of the angel investors for that group, but I was also a presenter for a project where we're applying AI to cancer clinical trials.
Right.
So as one of the angel investors, obviously I couldn't be in there for my project or my startup, but you know, I get the slide decks with everything, so I'm looking through it, and it's like. So the pitch, just to give you, so we were pitching our project, Kurova, where we're working with an oncologist, and we have two computer science students. We have a senior, Caleb White, and then a junior, Ben Wren, who are interns for us. And then we have two computer science alum from here who have master's degrees from Concordia who are also on the project. And we're hoping to sell the company for about $1 billion. Pretty legit stuff. So we're up there giving our pitch for round one funding. But there were still only two groups there at the big pitch event, and I was not happy with their open bar either. It was just not good. But in any case, the other group was about the medical problem was about people who sometimes have problems keeping all of their um, feces inside their body. You know, as you get older, you start running into issues. And so they had various tools that they were reviewing. This is what's available on the market right now and how each of them work. And then they passed around their device as a show and tell. So I'm wondering, and I'm sitting there like, how am I going to be able to keep a straight? Like, it's legitimately a real problem. So it's like, it's an important thing that needs to be discussed, but still, you know, I'm like a 5-year-old. So in my head, we're bouncing.
The rod that goes up.
Yeah.
Train your muscles.
Right. Apparently, as you're working on your pelvic floor muscles to strengthen them to reduce the issue that you might have, it's hard to it's hard to get just that one muscle working. So there is something you insert up there to start exercising, and then you get it has a long thing with a balloon on it that gives you visual feedback as to whether or not you're squeezing. And that's the device they were handing around. We were passing it around the audience.
Yeah, I mean, it's like really cool that he's involved in that.
Sure. And his dad was like one of like the main presenter as they're passing the stuff around. And so then I do the joke in reverse, like, okay, so one of my students' dads said multiple private part words within a 30-second period, and you work yourself backwards from there. So anyways, that was entertaining.
Or he was a professor here. He was
yeah, he said, and then he's got Parkinson's. Because I have tremors in my left arm, and I noticed his tremors, and then we were talking about it afterwards. They don't think mine's Parkinson's. Mine's an essential tremor and funny. But I sometimes have problems typing. My hand's shaking all over the place.
Yeah.
Yeah. Calms down with enough alcohol.
Yeah.
All right. So let's get rolling. And as I said, so we do not have class Thursday, right? Wednesday after 4 p.m. is when class, your break officially starts. Is that a true statement? No class Thursday?
No, I think there is class on
Wednesdays. I think there's class Wednesday up until 4 p.m. officially. Sometimes teachers will cancel their class, but I think technically there are classes on Wednesday until 4 p.m. Here, let's just confirm this.
Wednesday at 4:45.
Yeah, well, when the students leave is unrelated to when there's actually,
I would be leaving much earlier if I didn't have class.
I understand.
So, yeah.
Well, let's confirm it here just so we know. Well, frankly, so I know whether I need to show up here on, well, obviously Thursday's Thanksgiving. We won't have class on Thursday. So that's, I guess, obvious. Thanksgiving break, it lists Wednesday through Friday. So it lists the whole week. So maybe Wednesday, there's no classes. So, yeah. So we won't have class Thursday. I won't give you homework over Thanksgiving break, but we are going to talk about some important things today. So, don't devalue these things. Okay, so last time we started talking about interfaces a little bit, and then we were rolling it into something else. And, we were mentioning something about this. So the interface we're looking at is the runnable interface. Remind me, what is the purpose of an interface in an object-oriented language? What problem do these things solve? Got nothing? Yes, we did. No, we ended class talking about threads, like just introducing threads. I probably was talking about USB standards or something. So, because we went and looked at the interface. We went to, we did Java runnable. It was actually already open. So we see that we have this interface called runnable. And it shows us here's all these classes that implement runnable. And one of them is this class called thread, which is what we're going to be talking about. All right. And so remember now? Yeah. So runnable has a single method in it called void run. Well, it returns nothing and it's called run. Now, so what an interface says is anybody who's going to implement this interface, in order for them to be compatible with the interface, they must implement all the methods and fields that the interface dictates they must. So they have to have those things. Because an interface, when you create an interface, well, let's not worry about creating an interface, but when you bring an interface into existence, so let's go into, actually, I'm already here, right? I need to be right in here. We already started doing this MPC thing. I started writing some stuff in here, but let me just do, I'm going to take that out. So we're going to say NPC extends entity. So we already had talked about this as our inheritance stuff, right? Unrelated to interfaces. So we'll leave it in there for now, but we're going to say this guy implements runnable. All right. So we're going to say that guy implements runnable. Oh, we got to. All right. All right, so it implements runnable. So in this case, we are advertising that we intend to be compatible with runnable things. And to be compatible with runnable things, we have to follow all the rules of runnable. And that rule, the one single rule for the runnable, is that you must have a run method. All right, so in here, I do not have a run method, correct? Now let's go and check entity to make sure entity didn't have a run method that we are accidentally getting. It does not. All right. Oh, actually it does currently because we said extends thread, which comes with a run method. So let's just take that off. So an entity is its own little thing. It doesn't have a run method. So we are advertising for the moment, we're advertising that an MPC implements runnable. And runnable says you must write a run method. It's different than inheritance in that when we say we're implementing runnable, we don't get the stuff from runnable like we would with inheritance. When we extended entity here, MPC gets everything that entity already has, and then it further differentiates itself. When we implement interfaces, we don't get anything other than a set of rules that we have to abide by in order to legally implement that interface. That makes sense? So if we were to run this right now, it's going to say NPC is not abstract and does not override abstract method run in runnable. So we have to write that is what it comes down to. So if we just put in here a public void run and had it do nothing, for example, now we'll be back to that other error about rat. All right, so the error about runnable disappeared.
Do we need to include our supervisors? Are you just?
I'm doing an example right now. We'll get to this. So what we're doing is we're introducing the idea of interfaces. Interfaces allow us to say something is compatible. I use the example of USB. So there's a zillion different companies that make devices that plug into your USB port, right? So they have to implement their device in terms of the things that USB can do, right? And there's going to be a list of here are the 10 things that every single thing that claims to be USB compatible must do. And those devices need to follow all those things. Otherwise, they might not work that well. You know, we've seen that before, like when Apple comes out with a new cable that feels very proprietary, right? And even though it seems like, oh, this is just a normal plain Jane cable, it becomes difficult for third-party companies to make those cables. Because what Apple does is they don't publish the requirements for compatibility with their port, with Apple's proprietary Thunderbolt port, for example, what came before they were forced to switch to USB-C for the phones. Because now USB-C is a standard that Apple doesn't control. But Apple controlled the standard for their little Thunderbolt port, and they didn't advertise that. So any companies in the early days of that, if you were to buy a third-party cable, because Apple charges, I think, roughly $1,000 for their cable. I'm rounding down. So, so if you were to buy that cable from Apple, it was very expensive, where a third party might sell the same cable for $4 or something like that. But those cables were not very trustworthy. Many times you'd buy it and it didn't work. Or it would allow for charging, but not communication. And some of those older phones you used to back up through iTunes and stuff like that on your computer. But regardless, what we're talking about with interfaces is compatibility for a core something. All right, so if something's going to be USB compatible, it's going to have a list of things it has to be able to do if you are going to advertise it as being USB compatible. All right, so now the follow-up to this is we're actually going to get rid of our implements runnable thing here. So we're going to get rid of that. We're going to get rid of run. Let's just get this back to a working state, because then I want to talk about threads today. That's going to be today's lesson. And we're actually going to do it outside of our game. I'll do it here inside the project, but I'm not going to mess with any of our game objects. So let's see. The rat problem was in dungeon, line 32. Yeah, this guy. This is when we were starting to create NPCs and stuff like that. So I'm going to get rid of that. Let's just get this back to a running state. Same thing with player. Did we go and make players a extends entity, which is fine, but a player doesn't have a start method anymore because it's no longer a thread. Okay. And you don't have to worry about the stuff I'm doing here. I'm just, we'll end up redoing most of this stuff when all is said and done. Okay, so we have a working game again. We can move around, yada, yada, yada. Yeah, because it was relying on some thread stuff that we haven't finished implementing yet. So I just wanted to get this compiling again, because we're going to do some test stuff today to talk about threads. So for the moment, we're going to kind of put the game on hold, but we're going to work inside the same project and we're going to talk about threads. All right. So I'm going to create a new file here. And I'm just going to call this guy worker.b.java. All right. And we're going to make this class worker B. And then it will have a constructor called worker B. And for right now, it's going to take in nothing. Let's actually go ahead and just, for the moment, since I'm going in this direction, we're going to say a worker B will have a name. And the constructor will take in that name. Okay. This is just a plain Jane class. We haven't done anything special with it. A worker bee is not a thread. It doesn't implement runnable. It's nothing new. Okay. So now let's talk about threads. All right. Now, previously, we talked about blocking code. That is, let's assume we have a scanner that we're wanting to read something in from the user. So back here, for example, if I go and I run driver, it is sitting here waiting for it's gonna. So right now, scanner is saying, input line equals input dot next line, I think is what we called our variable. So it is blocking the rest of the program. This program cannot move forward because it's waiting for our user input, right? So now while we're sitting here waiting for our user input, deciding where we want to go, we'd love for our game for there to be the chance that some rat comes wandering into the room while we're sitting here making our decision. That means that other parts of our program need to be active, need to be able to be running in order for this to be possible. Yet right now we are blocking everything because our program is a single threaded program. There is one thread of execution in our program right now, and we're currently blocking the road. All right. So we would like there to be multiple ways of having things happen in a program. So let's go back in history a little bit, and we're going to talk about some problems with this. So let's call this overcoming blocking code. When we need other things to happen in our program, while some line like user input is blocking until the user enters something and presses enter or presses return, we need something else that can run in the, we'll call that background. All right, makes some sense. Historically, this was done with multiple processes. All right, now let's talk about what processes are. CPU scheduling in operating systems. All right, so all of you have computers that you have multiple programs open at once on, right? We take that for granted today. By the way, they haven't always been that way. If you go back, so my first computer was in 1984, 85-ish, and it was running just DOS. So you only had a command line and you could run a single program at a time. Now, over the years, eventually we came out with Windows, the Microsoft Windows, various versions of that over the years. But the first version of Microsoft Windows did not let you run more than one program either. You had a nice user interface. You can double click on something, but when you double clicked on, back then it was called Microsoft Works, not Microsoft Word. But when you clicked on Microsoft Works or Edit, which was your word processor before any of those things was just called Edit, and it was blue. It was a blue background from the command line. You'd launch it. But anyways, that program would launch Microsoft Works that you double clicked on. And now that was the only thing running on your program at any point in time. Now for many years, that was the case. And then the first consumer operating system that came out that allowed us to have multiple things running at once was Windows 95, which came out in late 1995. So before that, there wasn't a such thing as having more than one program open at a time. Did any of you have, actually, let's think about this. What year did the first iPhone come out? I was about to ask, did any of you have the first iPhone? Wait, 2007 was the first iPhone? You were born in 07? All right. Did anybody have the first iPhone? I know a couple, you're older, right? But there you go. So it doesn't matter. I was just gonna, so very first iPhone. Now, all of you right now, you take for granted that you can get your music playing on your iPhone and then go and check your email. And, you know, you have multiple things running at once or seemingly running at once. The mobile devices kind of do some tricks behind the scenes. If you are in our scholars program and are going to take the graduate level mobile computer architecture class with me, we talk about some of those tricks that get done behind the scenes to to maintain battery life. But in any case, that very first iPhone that came out, this is before the App Store was a thing. Very first iPhone that came out, you could not do two things at once. If you wanted to listen to music on that thing, which you did through your iTunes app that was on there, that used to be, iTunes isn't even a thing anymore, is it? No, it's just called Apple Music, I think. Okay, so when that came out and you wanted to listen to music, it became your iPod effectively, but that was the only thing you could do on there. Now, when after the App Store went live, then you still could only do one thing on there at a time initially. Now, and keep in mind that when Android first came out, which was about a year and a half or so after iPhone first came out, now iPhone had their mobile operating system that they built called iOS that was running on there that did not support multitasking. Now, at the time, because you said 2007 is when this thing came out, the first iPhone, keep in mind that is 12 years after we had multitasking on desktop computers. So everybody had already become very accustomed to, I want to run multiple apps at once. So it was a complaint that people had in the early days of iPhone. Well, about a year and a half later, Android comes out, and right off the bat, Android has multitasking. That makes Android better, right? No. Keep in mind, this is the very early days of people running around carrying effectively computers in their pockets. Those had batteries in them. They had smaller batteries than they have in them right now, or older technology batteries than we have in them right now. So yes, Android had multitasking day one. Does anybody know why they had multitasking day one? What operating system is Android based on? It's based on Linux. But it wasn't a new operating system that they wrote from scratch for mobile. They took an existing operating system, Linux, and shredded it down, took as much stuff off of it as possible that didn't need to be on there so it would fit on a mobile device, but it was still at its core running the Linux kernel. And the Linux kernel is the actual operating system. So that's what handles your memory management. That's what handles your CPU scheduling. Process management is what we're going to talk about here today. So it was using a really, really good and stable desktop operating system on a mobile device that's fully supported multitasking. So all their commercials would have been promoting how it supports multitasking out of the box, yada, yada, yada. You would think if I have the thing plugged in, it would, whatever. Maybe only if it's plugged into the HDMI instead of this USB thing. Okay, so, but in any case, So all their commercials were bragging that they had multitasking and Apple didn't. And Apple would say, oh, it's because it would be bad for battery life, yada, yada, yada. So the early Android devices were absolutely terrible. They got like 20 minutes of battery life. It was bad. It was really bad. There would be like joke. I guess back then it was maybe the early days of memes where people had like car batteries in a backpack carrying it around to keep their device charged. So in any case, there was a similar thing. How many of you have ever used Flash? Been to a website that requires Flash? All right. So this is before HTML5 became a standard, because there was a lot of press back. So basically, probably around a similar time period, 2007, 2008, 2009, Flash was pretty common on websites, because basically any website that had interactivity, like Yahoo used to have Yahoo Games where you could play blackjack and stuff, and they probably still have a rendition of it, but that was all written in Flash back then. So this idea of Flash capability on your smartphones was considered important. Now, Apple to this day has never supported Flash. Android supported Flash day one, and they would go around bragging about it, yada, yada, yada. Now, did any of you ever have an Android phone that had Flash on it? So back when I first started teaching this, that people were commonly had those phones. I've been teaching for a few minutes. This is my 25th year, but 25th minute, yeah. So in any case, they would brag about having Flash support, but nobody used Flash on their phones for two reasons. One, it was not a good end user experience. It didn't translate well into that small screen, because most of our websites didn't scale down. The sites that had Flash on it, they didn't scale down to smaller device things. So you would go to that website, you were running the mobile version of Flash. This is the same version of Flash that runs on laptops. That ran on laptops. So it would burn your battery even quicker. Bad user experience and destroyed your battery. Now, back then, what I would tell students is, I'd say, oh, how many of you have run Flash on your laptops? Laptops, big batteries. Back then, the average battery life on a laptop was maybe something like 3 to 4 hours, something like that. That was considered good battery life for a laptop. But most people would never do this experiment. So let's say you had a laptop with a battery life of 4 hours, and you went to you unplugged it, fully charged. You went to Yahoo Games and just sat on the page because Flash was running actively on the page. Your battery life just became about 40 minutes. Going to a website. Okay, Flash ripped through the battery. Now, it doesn't mean that it was a bad technology. It was made by Adobe. It was a good technology. It was just written at a different time. Okay. Laptops were not a super common thing. It was written for computers plugged into a wall. Just like Android was written just like Linux was written for computers plugged into a wall. Most of our servers online today are Linux based. They're Linux-based servers. I'm guessing it's like 75% Linux, 25% Windows, ballparky. A couple of years ago, Apple had a Mac OS server that I thought that was going to be a thing, never became a thing. so it's either Windows servers running IIS for their .NET web stuff, or it's Linux. Those are your two servers that are out on the internet today. All right, so anyways, a lot of these early wars between Android and iOS were very marketing based. iOS was the superior operating system. Forget about whether you loved or hated Apple. They made choices that were mobile first choices. I have a small screen relative to my laptop or my computer, and it's running on a small battery. So they made decisions that were based on those facts. where Android did not. Android was in a rush to get to market because they saw the success Apple was having. You know, you go to the very early days, the company that probably got hurt the worst from the success of Apple, at least early on, was Verizon. Anybody know why? Okay, so now, so iPhone, obviously it's a cell phone, right? Well, when iPhone first came out, as Apple tends to do, they had an exclusive agreement with a cell phone carrier. And back then, there were only really two cell phone carriers that they would have talked to, Verizon or AT&T. Well, they went to Verizon and they offered them the exclusive deal to be the exclusive carrier of iPhone. Because keep in mind, this was like kind of the birth of data plans, of real data plans on cell phones. So they had this agreement with them for unlimited data on your cell phone. So they went to Verizon, and Verizon said, real money's in BlackBerry. Back then, Blackberries were popular. Windows had a smartphone thing too, but everybody had Blackberries, and it was all about the physical keys. They wanted the physical keyboard. But so they went to Verizon. Verizon said, no, get out of our office. So Apple went to AT&T. AT&T said, sure. AT&T made bank. How many people are Apple fanboys on Verizon who bailed on Verizon to go over to AT&T because that was your only way of getting an iPhone? It was a poor business decision in hindsight for Verizon. I want to say it was maybe like 3 years later, maybe two, when Apple finally was available on other devices, or other carriers, rather, other cell carriers. So for the first couple of years at least of iPhone existence, the only way to get it was on AT&T. So maybe day one, when it wasn't proven yet, you didn't have people bail in bulk. But pretty quickly, when it became clear that, okay, this is kind of the future of phones, we want one, AT&T made a lot of money off that. So just kind of interesting history stuff with that. So now what happened is, so year two of iPhone is when they released the App Store. And I don't remember, some of you have heard the stories of one of my businesses was writing apps on the App Store day one. So that's when I had the dice rollers and the real-time stock quote stuff that made a lot of money because everybody and their brother bought every app on the App Store the day the App Store went live. You know, my dice roller was not that fancy. I actually use it when I teach mobile application development. Now I use it as one of your homework assignments. So you're writing a homework assignment that you have like 2 days to write, or maybe it's over a weekend, that you're creating an app that once made $3 million. Not so much today, but that was a reality back then. So in those time periods, as the App Store went live and you started having developers getting in there, starting to run, write their own apps, and we started having this transition into users expect to be able to listen to their music and check their email at the same time. Those should be things that can happen. So Apple's approached this. Apple even today has kind of pseudo multitasking on iPhone. But what their initial approach was, they said, okay, what we're going to do is we're going to say, here are like the 8 things that an application might want to do in the background. All right. One of them might be playing music. So what they did is they allowed an application, as it was going into the background, they allowed it to say, okay, I want to stay alive in terms of that one thing. So they could hook, if you were, Pandora was the popular one back then. Is that still a thing? Pandora? It's lost it. Oh, Spotify is the thing now. Well, Pandora was the thing back then. So, as Pandora was going into the background, it would hook into the operating system's ability to continue to play music. So it was kind of like put to sleep in the background, except for that little music playing ability. So now it was still playing. So it was kind of Apple's approach to pseudo multitasking, where Android still always had the bad multitasking. Over time, Android moved to a pseudo multitasking model, like Apple did. From an end user experience, the stuff is all running at once. You know, when you're using your phone, you typically aren't starting a big download and then switching to another application. Though that's just not one of the things we do on our phone, other than like downloading an app or something like that. That's something you might do on your computer, where you have a Steam game that's 130 gigs that you're going to download over the next 14 hours. You'd like to still be able to use your computer, so we have real multitasking on those computers. All right. So in any case, the guy who might handle multitasking is our CPU scheduler. All right. So this is a sub-program inside of our operating system who has to say, okay, we have a bunch of programs running on the computer. Each of these programs is a process. That's what they are. So Microsoft Word, the reality is, well, there was a point in time where some programs would have more than one process. That's what we're going to talk about here. But so CPU scheduling today is much, much, much more complicated than it was years ago. Because for a long time, we had single core CPUs. They didn't call them single core because it was a CPU and the idea of multi-core wasn't a thing. All right. Why did we create multi-core CPUs? We couldn't figure out how to make them any faster with single cores because of heat. So we just added another core. And so we had two things running at a little bit lower speed that gave us the same level of heat, but now you technically can do two things at once. So for every core you have on your CPU, that's the number of things that actually can happen at the same time. When we had single core CPUs, we relied on this idea, like we've talked about in here, that computers are really fast. Even computers back then were really fast compared to human beings. And keep in mind that our software back then was less demanding on our CPUs. As our CPUs have gotten faster, we've been able to write software that takes more and more advantage of them, just like our video games. If you look at a video game from the 90s, the graphics are not in the same category as video games are today because we have these massive GPUs with a whole lot of dedicated power in them to drive 4K at 60 frames a second or 120 frames a second with super high resolution textures and all this stuff. So we've grown up some, but back then we had CPUs with a single core. So technically it could do one thing at once. And what it did is it relied on the idea of like, hey, I'm really, really, really quick. I want to just convince the end user that more than one thing's happening at once. That's what I have to do. So they would say, I'm going to give, so let's say you had 4 programs running on your computer. You're going to say, I'm going to give you a little bit of time, then 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 back here. But they were doing it super fast. So we didn't even notice. And when we say a little bit of time, it's like, how many instructions do they get when they get onto the CPU? So the CPU is like a ride at Disney World that you're waiting in line to get onto it. And actually, it's probably more like kind of like a hotel room or something. Because of this thing called context switching I'm about to mention. But in any case, you're waiting in line to get access to this resource. And when it was your turn, the very first time you got on there, you started at line 1 in your program. And I'm talking about the assembly language side of your program. So remember when we looked at Hello World for Linux, that assembly program? So you would get so much time on the CPU, and depending on how long those instructions took, or if you had an instruction that was a blocking instruction, you would do as much work as you could possibly do on the CPU as you were allotted, or until you couldn't do any more work until you got something from input output. And you kind of saw this probably early on in the semester. I probably wrote a program that had a for loop that counted from like 1 to 100,000 and gave you the result, and it ran instantly. And then I did a thing inside the loop where I just printed the current count, and it took a lot longer to run. Remember us doing that? Okay, so what was happening there is that program was not taking full advantage of its time on the CPU. It was getting onto the CPU and then almost immediately having to it was incrementing a number, and then all of a sudden it's like, oh, I have to send something to the user. That's IO. IO is something that's handled by a different part of the operating system. So they had to then jump off the CPU to go do IO stuff so they didn't take full advantage. All right. But in any case, what would happen is, if we forget about the IO thing, a process would sit there, wait for its time on the CPU, would get access to the CPU, would do a bunch of stuff until it got kicked off. If it was its very first time on the CPU, it would get there, would do all its stuff, and while it's doing its stuff, what it's doing is it's loading things into these hardware registers, which are buckets of memory that are on the CPU. So the CPU has these little tiny things like, okay, it's going to hold a number, a 32-bit number or a 64-bit number, things like that. Now, as soon as your time was up, a process had to say, okay, well, I didn't finish running yet, so I need to go ahead and remember what the current state of things are, okay? Because the next guy coming in is going to overwrite all my stuff. So I have to remember that and package it up, kind of put it in your suitcase. All right, then you get off the CPU, you go and get back to the end of the line. Next guy comes in, overwrites what you had there, blah, blah, blah. So now when it's your turn again, you get onto the CPU, you reset all the hardware registers. I like to think of it as kind of like unpacking your bag. You get into the hotel room, you unpack all your bags, you put them away in the drawers, all that stuff. You have your, 3 milliseconds on the CPU, which is, that's quite a bit of time in computing time, but not very much time to us. Then you immediately have to pack your suitcases back up and get back in line. So that was the rotation that would happen. That's the job of the CPU scheduler. CPU scheduler is to keep things getting on and off the CPU so that they all appear to be running in real time for the end user. We don't know the difference. Yet they were each getting just a little bit of time, and it was just this round robin thing. Now, as soon as we started getting CPUs with more than one core, now technically the CPU scheduler can say, okay, well, I have 2 different places that I can send them. So now it's a little bit harder job because you're scheduling for 2 places. Now, what would happen is programs, when we still only had 1 core, and a good example of this was Photoshop. They did this. They were sneaky, and they would have done it was kind of like a cheat code in a video game. So Photoshop wanted their programs because Photoshop was taking quite a bit of resources on a computer back then, in terms of percentage of the ability. Well, but I mean, now you could have multiple cores, lots of RAM, so you notice less. But back then, you would feel like your other programs were sluggish because of Photoshop. Well, and the reason for that is Photoshop would make a twin of themselves. So they actually were more than one process. So we used to have something called the fork system call. We have to be very careful about how we enunciate that word. So we have the fork system call. And the way the fork system call would work is you would write a single program. And then you would get to a point in your program where you're saying, okay, I need to have 2 things happen at once. Or I'm going to have something blocking here, and I want a helper, a worker bee, like we're going to be making. I want this guy to go off and do his own thing. So we're going to have the original parent process create a child process. And the way this used to work is it would all be inside the same program. You would make the call to the fork system call, which would talk to the operating system and say, give me a duplicate, a clone of myself. Now you have 2 versions of that program. And each of them, right after you make the fork system call, you have an if statement that says, ask the question, am I the original or am I the child? Which one am I? So if you were the original one, you would go down one path in that if statement and keep doing the stuff you were doing. If you were the child, you would like, oh, I'm the clone, really? But then he would go off and do whatever other things. And they could keep doing this. So you would have Photoshop having 3 or 4 processes running, which meant they got 3 or 4 times the power or times the time on the CPU. So they were hogging the CPU. Ball hog, like from basketball. So anyways, operating systems locked that down a little bit, but that was the way that you could have a single program bypass a piece of blocking code. So if we wanted to have our rat being able to wander into the room, old school, we would have had our main thing, call the fork system call, which would then give us another process that could go off and control the rat. That was his job, is driving the rat around the dungeon, whatever, while this guy over here is still waiting for the user to enter in their stuff. And even in a single core processor type thing, those two processes were each getting their own CPU time. So, and keep in mind the CPU is trying to run as fast as it possibly can so that we're faked out that all this is happening at once. So, that's what would happen. And then if you wanted to have multiple things, you would call fork again, so the child could make a duplicate of itself, so on and so forth.
So the fork system, when you write a program and that program creates like a duplicate of itself, so that way it can run two things at one time.
It can, from a user's perspective, two things are happening at once. But from the operating system perspective, there were two separate processes that the operating system didn't care that they were related to each other, but they were two separate things that would get scheduled on the CPU. So they were getting double the CPU time.
Because they were duplicates of each other.
Well, because they were two processes. Doesn't matter that they happen to be duplicates. From the operating system's perspective, one guy, poof, became two guys. Doesn't matter that these guys are the same guy. It means that there's two separate things. It's as if they launched Word and then launched Excel.
Okay.
They were both getting CPU time, so technically that program was getting extra CPU time. So this is how we used to pull it off, but we see that this is problematic, right? We also had, if you think about the complexity of CPU scheduling, now there are other system calls that let these two processes talk to each other. It's called inter-process communication. Sometimes you'll see it as IPC, all caps. So maybe this program needs to tell this program that, oh, I have finished this task, so now you can go and read from that file because I finished writing that file or something like that. So there's communication happening between these guys. Well, if you're the CPU scheduler, you would have to know that, okay, I can't let this guy onto the CPU until this guy finishes what he's currently working on, because this guy is reliant on this guy. So it makes that scheduling thing more complicated. Okay. Then obviously, as you keep adding more and more and more cores, now all of a sudden, sure, I have a free core over there, but I can't let this guy go onto that core because he's waiting for this guy to finish his stuff. So even though I have processing power available, I can't load them yet. Makes some sense? So it gets more and more and more complicated. So at least part of that complication has to do with this multi-processing thing. So that's when, so we're going to say fork system call made a clone of the process, which was a brand new process itself that received its own CPU time from the OS. This created, let's call it, performance problems for the other applications on the computer, because the program with multiple processes was getting more CPU time. All right. So in walks the thread. So the idea here is that we're looking for, oh, was there a, oh, I thought there was a question. So what we're looking for here is, how do we still give us the ability to have more than one thing happening at once, whether it's actually happening at the same time or we're just tricked into it's happening at the same time, doesn't really matter, right? As long as our experience is that everything's happening all at once and we're happy. But we want to get rid of this problem of it bogging down a program having, first of all, the ability to maliciously bog down our computer, because this is how early hacks worked. How many of you have heard of a denial of service attack? All right, do you know what it is? What's a denial of service attack? Okay, let's say that's close. I'll tell you a little more about it. But so what's a DDoS, distributed denial of service attack?
Packets over time make the server less effective.
No. So go ahead.
The attack in the first episode of Mr. Robot. That's all I got.
Oh, okay, that's all you got. Now, so when the internet came out and we started having the ability to have our computer talk to other computers, we that would, back then is when we would have this idea of a denial of service attack. A single computer is overwhelming another computer, and we could just say somehow. You gave an example of sending too many packets or whatever. We don't have to get into the weeds of that. Just somehow one computer was overwhelming the server so that either the server became really sluggish, it was a bad experience for anybody else trying to connect to the server, or whatever. Now, as computers started being able to talk to each other, we started having this idea of a distributed denial of service. So this hacker person, whatever, they would get their little program that attacked that server. They would somehow get it on 1,000 different computers. Could be they hid it inside of a PDF or something. This is why they say don't click on certain things, because it's going to load stuff onto your computer. We have a lot more protections at the operating system level now than we did back then, but those protections were put into place once these started becoming problems. So now you have 1,000 computers who are all running that same program that is attacking that single server. That is a distributed denial of service. And this was actually kind of some of the interesting things. This must have been in early 2000s, maybe. There was a website. I think the website's actually still alive. It's called distributed.net. Last time I checked, it was like a super old site. Like they hadn't updated it since the time I'm talking about. Distributed.net. Yeah. So this guy is he's got some age on him. I don't think this is any different than when I used it. But in any case, distributed.net took advantage. What it was trying to do is it was trying to stress test encryption algorithms by having what you would do is you would go on there and you would download their client, run it on your computer, and then you became part of the network of computers that were trying to solve a problem. All right. So the problem you were trying to solve is breaking an encryption algorithm, the things that were locking down passwords or whatever then, because effectively a brute force attack to a encryption or a password. Let's say you have a password that has 8 characters, lowercase, uppercase, punctuation, and numbers. All right. So what is that? 52, 62, let's just say 70 possible characters that exist in it. And passwords, let's just say had to be 8 characters long, exactly 8 characters. So that means you had 72 to the 8th power unique passwords that could be created. Each character in it you would pick one of 72 options, times one of 72 options, times one of 72 options, so on and so forth. All right. So a big number of unique passwords that were possible. Now, if you had a single computer checking password 1, password 2, password 3, password 4, yada, 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 you would take a long time. But now if you had 1,000 computers that were working on the same problem, and they each came to a password server and were handed a collection of passwords to try. Make sense? then they could work their little part of the problem. So you distributed the work across a whole bunch of computers, and all of a sudden you could do it much, much, much more quickly. Now, the funny thing that happened back then is the U.S. government was working on a encryption algorithm called triple DES, DES, and they claimed it was uncrackable. Strongest encryption in history, yada, yada, yada. Distributed.net cracked it in like a minute and a half. So something like it was pretty embarrassing. They didn't say it was uncrackable after that, but we've had many, many things better than that. Today's encryption is RSA. All of our encryption is RSA, which if you were at that pitch event where I gave this quick little talk about it, RSA is based on top of a difficult math problem. If you take two large prime numbers, and as prime numbers get bigger and bigger and bigger, it's hard to even know if they're prime. So there's algorithms for determining, is this number probably prime? Remember, a prime number is a number that's only divisible by itself in one. That means if you have a gigantic number, technically you might need to check every single number between 1 and the number itself minus 1 to see if it's evenly divisible by any of those. Technically, you can squeeze that down a little bit by using square root. You don't actually have to check all of them, but you still got to check a bunch of them. So you would take this prime number and this prime number, you'd multiply them together to get this gigantic number. Now, the security of RSA is based on your ability, if you're going to try to brute force attack RSA. If you already know the password, you're good. But if you want to brute force attack RSA, what you need to get those original 2 prime numbers. So given a gigantic number, tell me the 2 prime numbers that were multiplied together to give you that number. So you're factoring. It's called prime factorization. And prime factorization on a number that large with numbers that also are prime is really, really, really complex. To the point that if we were going to crack today's RSA, it would take just all the computers on Earth working in tandem, distributed, to try to crack that would take us 3 trillion years. Secure? But like I said, my research area is quantum computing. If we have a stable quantum computer, 3 trillion years becomes 8 hours. That's interesting. That changes our faith in our security these days. And at some point in the next hour, you could have a computer that's announced today that can do this. But I'm working on my research with the Department of Defense deals with how do we get stable computers faster than some of our enemy countries might get it. So I guess we can abuse them, maybe. I don't know. They don't tell us what they're going to use it for. They're just going to use it. Go ahead.
Are we just basically waiting for that to nullify and that's all factored?
No. So we have other areas of research that are in the cryptography field. So if any of your cybersecurity people, there's other areas of research that are trying to effectively create quantum resistant encryption algorithms, kind of taking maybe RSA as a base and having different approaches where you have like rotating keys based on the clock and stuff like that. So it's a moving target, things like that. So, it's not like tomorrow this could destroy us. Well, if it happened tomorrow, it probably would. But we are actively working to the point where it probably isn't going to be a major problem. But at the very least, in this example, you see what quantum computers will bring to the table. They're not going to replace these guys because quantum computers are only good at a subset of problems. They can solve any problem that a classical computer can, but you might as well just use a classical computer rather than using this thing that costs zillions and zillions and zillions of dollars. Quantum computers are really good at solving problems that are distributed. Things that we're talking about today, where you can divide the work up. Quantum computers can divide the work up even within a single qubit, where from our perspective, you can have a quantum computer can do, it's more than this, but let's just say it can do 1,000,000,000,000 things at once when you're working on something. It's like having 1,000,000,000,000 computers all trying to solve the problem. And like I said, it's actually more than that. It's ridiculous. It's really cool. I like to think of it as like God's Legos. This is how reality is built, is with quantum mechanics. Quantum computing is us stupid humans playing with God's Legos, trying to leverage them to solve problems that we want to solve, when it's actually the tools that he used to build reality. It's terrifying and fun and all this stuff all at the same time. So, coming back full circle, and all these things were related, but coming back full circle, what we really need is, I was in the middle of a distributed denial of service thing, so we got to finish that. So with the distributed denial of service, what would happen is, so we're still talking about processes. This is the lead up to the need for threads. So what a distributed denial of service would do, or even just a normal denial of service. So let's say that I had, I had a single computer, and I've tested this. I haven't broken into other people's computers, but I've done it to like my own server testing stuff, years and years and years ago. But let's say you had access to that computer, whether you legally had access to it or you somehow gained access to be able to log into some Linux server somewhere. You could write a program that had an infinite loop, while true, create another process, and by using the fork system call. And what did that guy do? He had an infinite loop that created another process. Well, what did that guy do? He had an infinite loop that created another process. Most of our modern operating systems, the number of processes that can exist on the machine at once, the number of unique process IDs, PIDs, is 65,536. Recognize that number? 65,536 is how many bit value? 18. That's not even the power of 2. 16. So a 16-bit number, 2 to the 16th power is 65,536. So remember chars, the Unicode character set is 0 to 65,535. You guys don't have these numbers memorized? Finals all this. Memorize everything. It's just going to be. All right. So in any case, just using a number, maybe some modern operating systems have bumped that up to 32-bit. So 2 to the 32, which is 4.2 billion-ish, something like that. But regardless of which of those two it is, the problem is still the same problem. So a single computer can have 65,536 unique programs running unique processes running at once. Now, some of those processes are going to be the programs that the users are running, Microsoft Word, Outlook, yada, yada, yada. But then you have a whole bunch of little programs that are running behind the scenes, like doing log files, cleaning up memory. If you were opening up your task manager in Windows, you'll see there's like 50 things running. So those are a whole bunch of processes. But you have a maximum of 65,536 unique processes. Now, if you're a single user on a Windows machine, you got plenty of space, right? But if you have a computer that is a multi-user computer with a whole bunch of people using the Linux server at once, you probably are still fine, but you will have a larger number of processes running at the same time because you have multiple users all trying to run their programs. And that's why those servers have to have more memory, processors with more cores, all this stuff, because they need more resources because they're sharing them among more people. But now if I'm a single computer and I get access to that computer and I don't have any protections against me, I can literally write like a 3, 4, 5-line program, tiny program, that just keeps creating process IDs, keeps creating new processes, and keeps them alive because they're all in a while loop. And then what ends up happening is you get to 65,536 unique processes real fast. So at some point, what will happen is when one of your processes tries to call the fork command, it'll come back, it'll fail because the system is out of process IDs. It can't hand any more out. So now you have this program still running. It's not getting any more because we've already filled it. But now the system administrators can't save the server because they can't even open up a terminal because that would be a process.
Like, what's the max amount of processes?
65,536 is the maximum number of processes a modern computer typically can handle at once. But even the system administrator wouldn't be able to open up a terminal to go and kill off all those processes. You write a little script, go through any process related to this, go and kill. So a lot of times they would have to restart the server, which would possibly cause processes that were previously running, maybe experiments and stuff like that, that might take weeks to run or something, because these servers are usually designed to stay running for a very, very long time. All right. So restarting a server is typically the very last resort you want to have. You want to be able to get control back to it. So what they started doing is you could get access through a serial port on the computer. If you had physical access to the computer, you can connect into the serial port, and that would give you a terminal that you can then go in and hopefully regain control. But the point is that you can see that a single computer with the ability to create multiple processes could take down Google back then. Now our operating systems have all your stuff running in its own little, kind of like a virtual machine, its own little bubble. So you are allotted an amount of memory that your programs have access to, which then translates into, oh, that's HR. Maybe this is my last day. It's the head of HR too. I go to church with her. I'm sure it's fine. But in any case, you could see this as a problem, right? So modernly, what happens is we still have access to the fork system call. It's not that multiple process programs are now gone, but we have guardrails on user space. So if we're a normal user account, I don't know exactly what the number is, but it's not going to let us take over the whole computer with processes. Maybe the count is 16 or something like that, that'll allow us to spin up. And at that point, it says, look, this, you're doing whatever you're doing it wrong. Try again. So that's where threads step in. So what a thread is, we usually refer to these guys as lightweight processes that share the parent processes. Parent process is, I think that's right.
I think take off the processes.
But it's, oh, whatever. We know what it means. Lightweight processes that share the parent. No, it is.
It is?
It's that. It shares the parent process. It's a single process, but it's the process that belongs to them. I think this is grammatically correct. English guy who skips class. What do you think? Let's just roll with it. It's fine. All right. So anyways, all the child processes, we call them processes. All the child processes are sharing the CPU time that the parent gets. So they don't get to go off the guardrails. All right. So, and we call them a lightweight process because they are much smaller. If you think about a heavyweight process, something that, you know, the antithesis to this, the thing we've been talking about all class, this idea of a real process, that guy has a lot of baggage that comes with it because it's kind of like this giant SUV that is running at the operating system level. So it has to keep track of a lot of stuff. All right. So the data structure that represents, if we were building a class, a Java class called process, that class would have more stuff in it than a Java class called thread. All right. Because a thread only has to deal with the world in which it has CPU time it's sharing with its parent. All right. So it's much more protected. It's like your own little ecosystem. All right, but we call them lightweight processes, even though they're not actually a process. They're just behaving much like processes, but they live within the parent's little ecosystem, the parent's bubble. Now, modern operating systems, though, do have the ability, because we have all these cores, they do have the ability to step in and say, okay, there are some processes waiting for CPU time for the parent that can run because they're not reliant on something else. And because we have available cores, we will actually allow those processes to get some CPU time even when the parent is. So it tries to optimize. Modern operating systems, well, all operating systems, the CPU scheduler's number one passion in life is to keep the CPU busy as close to 100% of the time as possible. Now, typically, our average CPU is idle something like 94% of the time, which means you spend all this money on this computer and you have this super high-end CPU. You're comparing the Core i9 with blah, 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 level 3 cache compared to a Core i5. Both of them are going to sit there idle 95% of the time. So what might make you buy the more expensive one? If you are a gamer, for example, where you have your video game might spawn off 3 or 4 processes and you want those processes to run at maximum speed, that's when you might get the highest end CPU because you kind of treat it like a drag racer, right? You're only doing 4 things at once, but you're doing them fast. And that's going to translate into the performance in a super high-end video game. You are only going to notice the difference between a $400 processor and a $1,200 processor less than 1% of the time, even if you're in that extreme situation. Your GPU is probably the better place to spend your money. I mean, money's unlimited, just max out everything and move on with life. But if you had a budget, decide where to spend your dollars based on what's actually going to get you noticeable benefit. You know, usually it's RAM followed by CPU. It used to be hard drive speed, but now we have solid state drives that are they're all fast. They're not the bottleneck anymore. But in any case, the fix for all this is this idea of a lightweight process that shares the parent process's CPU time. So what we're going to do in here is we're going to use threads. Threads already implement the runnable interface. So threads are compatible with runnable. We don't actually have to think about the interface side of things. I introduced it so you knew if you run into this in the future and you have to make something align with a certain interface, what that means is you have to write all the methods that interface defines so that your program is compatible with whatever it's connecting to. All right. This happens actually fairly often in industry when you are working as part of a team and you have 3 different people on the team who are writing pieces of a program that need to talk to each other. There might be a core central interface that you all must play by so that you make sure that data can be transferred between those pieces. You kind of agree upon a thing ahead of time. All right. But we're going to use threads. We're going to use the inheritance model to say, I'm going to create something like an NPC, which might be a rat, that is a thread. So I'm going to extend thread, and then I'm going to override the run method, similar to how we overrode the toString method before when we were trying to make our things not show memory addresses. I'm going to override the run method to make it do the stuff that I want this NPC to do, which maybe is every 3 seconds, flip a coin, decide, do I move or not? If yes, flip a coin to decide which exit I take, and then move. And then you might wander into the room the player's in. Make some sense? All right, questions, comments, concerns, bribes?
Oh,
Bribe? Yeah, no homework over break. But we'll have a really, really difficult assignment the week we come back to catch up for all these assignments you missed, right?
no.
All right, have a safe trip if you're traveling, all that jazz. Don't get end of the semesteritis. You know, we have two weeks left. I think next week our last week of class before finals. So we only have 2 classes left. that we're meeting. So, and then the final we already discussed will be impossible.
Oh,
The final will be online, similar to the midterm. I'll put it up like at the beginning of the week. You need to get it in by 11:59 p.m. Friday. So you can decide when you want to slot it into your schedule with your other finals, but
so,
so, all right, have a safe trip.
like,
I'll have to decide once I start thinking about the questions.
oh.
It'll be very similar.